Quick immediate disclosure, I am not an analyst, and I have a real strong love-hate relationship with analysis, real analysis in particular. In particular, this was motivated for showing that for the finite geometric series to an infinite geometric series proof, that if the absolute value of r is less than 1, then the infinite limit of the absolute value of r, your common ratio, raised to the n, goes to 0. However, unfortunately, using the machinery that I am most comfortable with today, I cannot show that it equals 0, I can only show that it converges. It's a lot of hard work. But first, let's go and explain how it actually sort of would go to 0 just using intuition. So let's say we have r equals 1/2. Yes, r equals 1/2. And then I have an, a1, and then 1/2 here. I can, yeah, let's start with r equals 1/2, a random a1, and then we'll go and generate the sequence here. So we have a1, and next we have 1/2 a1, and 1/2 squared a1, 1/2 cubed a1, 1/2 4 a1, and so forth up to 1 to the half n a1. And I don't know, aside from number, I don't know how to describe, aside from just testing with a bunch of more numbers, that like 1/2 to the n, this sequence obviously goes to 0. So then that goes to 0, but I don't think that's a rigorous enough job, so I'll leave it at that. But now to go and show that this thing does converge, we need to go and, at the end of the day, appeal to the Bolzano Weirstrass theorem. Which I want to abbreviate as BWT, which says if a sequence is bounded, that means there is a particular number, real number, that is the biggest of all numbers or the smallest of all numbers, doesn't matter which one, and is monotone. Monotone means everything in the sequence is either completely increasing, like that, or it's either completely decreasing, going like that. But only like that. You cannot have this kind of like pattern, because it's doing both. It's gonna be simple straight line like this for decreasing, or simple straight line like that for increasing. Sorry, and then curve. But if that is true, then the subsequence which is basically a sequence inside a sequence, or a sequence that still keeps continuing to infinity, because we're looking at the long-term future behavior of the sequence an, so we can look at what happens next in the term. Then the subsequence converges. Okay, that's our star that we're going to use today. And unfortunately, I will have to confess over here, this is going to be very hand-wavy, or I can only give a skeletal outline because I'm not really good with infimum and supremum proofs, which is the way you describe these bounds properly in the speak of real analysis. Because they involve proof by contradiction, and I'm bad at it. But this one I can show that it is decreasing. In particular, for the following function, for the following sequence. Let an equal absolute value of r, to the n. And if we're going to go and be very nice about the function, about what the domain and the codomain set are, then this has the input of the natural numbers, and it spits out, we could say real numbers, but really it could be any set. The way to show that something is decreasing, this is the same thing as saying that an plus 1 is less than or equal to an. That's the key thing here, and that's the main use of what I'll be doing for this video. So, okay, how do we do this? We start off with an plus 1 is less than or equal to an. Then we minus both sides by an. This goes to 0, and now you have absolute value of r to the n plus 1 minus absolute value of r to the n. Yep, all good, all good. And now I can factor out an absolute value of r from here. Absolute value of r, n, absolute value of r. Sorry, I can factor out absolute value. Okay, so factor out absolute value of r to the n. So that goes here, and I get absolute value of r minus 1 less than or equal to 0. And now comes the final part. Use the assumption. This guy over here. From absolute value of r is less than 1, I can subtract 1 on both sides. And that just becomes absolute value of r minus 1 is less than 0. But the absolute value of r minus 1 is less than 0 is this corresponding factor over here. Boom. So then this is, we can't tell anything about this, but this whole thing here is going to be less than 0. So we have absolute value of r to the n times 0. It's less than or equal to 0. And we get 0 is less than or equal to 0, which is obviously true. And so from this, I repeat again, we've shown that Rn, or that the limit, infinite limit of n goes to infinity for a subsequence converges. Showing rigorously that I'll go to 0 will unfortunately require a lot more work, and you would probably have to go and pull out an epsilon delta argument, which I really would call an epsilon delta machine gun. And doing that properly requires careful manipulation of the triangle inequality, which is this guy over here. Boom. Sorry about that. Sorry about the upward pause. Yeah, and I've seen some things of the proof that involves logarithms and binomial theorem as well. But I just think that's too complicated and overkill. Though it's nice to see fresh, distinct subjects or concepts that we can manipulate around with. Anyhow, that's all I'm able to show. Sorry if this seems a bit like a cop-out, but this is the best I can do. I want to say what it is as not a lie. In fact, I have a possible feeling that my argument might be bullshit, possibly at the beginning, but I am very doubtful of myself. So please let me know. The place where I think I might have made an error is that over here. I've already assumed that the sequence is decreasing without really showing it that. But if that's the case, I really can't do stuff like equalities and equations. I have to think purely in terms of inequalities, and as I said, I'm really not an analyst. But I hope you enjoyed the video nonetheless. Thank you.